Hello, this is an exercise A-level mathematics, paper 1, and we are going to do the exercise number 12 on the paper 2019. This is the function 10 times the exponential to the power of minus 0.25x times the sine x. And the first part is to show that the x-coordinates of the turning points of the curve with equation y equals fx satisfy the equation tan x equals 4. So to find the turning points and find this equation tan x equals 4, we need to differentiate the function f and make it equal to 0. And since the function is a multiplication of two other functions, g and z, the derivative is g dash times the z plus the g times the z dash. This is the rule of differentiation. We are going to use the product rule, and we need to make it equal to 0 to find the turning points. We use the condition to find turning points. The first derivative needs to be equal to 0. And let's start differentiating the function f. The f dash will be the derivative of the first function e to the power of minus 0.25x, which give you minus 0.25 times e to the power of minus 0.25x times by 10 give us a minus 2.5 e to the power of minus 0.25x times the sine x. And we need to add the function e to the power of minus 10.25x times the derivative of the sine x. This is the cosine x. So we add the 10 times e to the power of minus 0.25x times the cosine x. Turning points is where the derivative is equal to 0. So we get this equation and we make it equal to 0. And rearranging this equation, we have an equation of sine x and cosine x. So we rearrange the equation as the following one. And dividing both sides by cosine x and also by 2.5, and the exponential cancel out, so we divide both sides by 2.5 and also we divide by cosine x. We have the equation tan x is equal to 4. This is the equation that satisfies the first derivative is equal to 0. The second part. Sketch the graph of h, which is the modulus of the original function, showing the long-term behavior of this curve. The function f is already here on this screen. That is going up, then it's going down, it's going up, and it goes towards the value of 0 in the long term. The modulus function will change only the negative part of the curve, and the negative part of the curve becomes positive. So the effect on the graph, it will be the graph you see on the right hand side. The negative parts are the parts of the graph that are below the horizontal axis. And these three parts of the graph will need to be reflected on the horizontal axis, as you can see on the second diagram. And this shows the sketch of the graph H. If you see, the heights here are decreasing, and then they go towards zero height in the long term. Okay, the vertical axis is the H, and the horizontal axis is the T here. And this is the sketch of the graph H. The function H is used to model the height of a ball above the ground t seconds after it has been kicked. Using this model, find the maximum height of the ball above the ground between the first and second bones. Maximum height refers to turning points on the graph, and turning points on the graph are satisfied using this equation we found in part A. So we get this equation and we solve the equation for x, and this equation gives us the turning points. Turning points are the maximum points of the H function. And solving this, we use the inverse of the tan, using the radians. We use inverse tan 4, and the first value is 1.3258. Because the tan function is periodic function and it repeats every 180 or pi radians. Another solution for the maximum value, it will be pi plus 1.3258, and this gives us a value of, yes, we need to add the two, so we have 4.47. So it's plus the pi. So we add these two values to find the second solution. And this gives us the value of 4.47 radians. These values are in radians. And to find the H, the maximum height, this is the time that produces the maximum height. So I need to use the function H, 4.47, and find the maximum height by substituting into the function of the modulus fx 10e and the value, the maximum value, it will be 3.18 meters. So here we say is that explain why this model should not be used to predict the time of each bonds. Now if this is a realistic model, the times here cannot be, the times between each bonds should not stay the same when the height of each bond is getting smaller. Obviously the times here are decreasing and it should not stay the same. That's why it's not realistic. And you may give a comment like this one. Any comment that reflects the reality, it will be an acceptable comment. Yes. And this is the exercise for today. Thank you for watching.